Hello, it's an honor to present my paper in SEC 2020. I'm Dus Cheng from South Korea, and I'm going to present my paper, Similarity-based Calibration Method for zero-shot recognition in multi-object scenes. Here are my contents in presentation. I'm going to present the backgrounds briefly, and then our approach and experimental results with conclusion. The traditional supervised learning requires a large number of training samples to be collected and manually annotated. But it is often challenging and time-consuming and often impractical. The transfer learning alleviates these limitations in scalability, including zero-shot learning. The objective of zero-shot learning is to learn a visual classifier for unseen classes in the absence of training visual data by using external knowledge. For the knowledge transfer, it is assumed that visually similar objects will be semantically similar as well. For example, horse and zebra have a same attribute, horse-like. Existing ZSL methods performs in the assumption that the semantic embeddings of the class labels of visually similar objects are closely located in a semantic space. So they focus on learning the capacity to recognize inherent visual characteristics of singular objects, such as shape or color or texture. However, visual similarity does not always represent a similar type of object. For example, in the case of identifying an unseen object, a plate, as you can see on the screen, it might visually seem like a mirror or a city due to its wide, flat, and rounded appearances. There is an obvious limitation in independently inferring a class label of an unseen object with only its visual information. But when we humans encounter this kind of object never seen before, we try to figure out its identity instantly using contextual cues such as the surrounding objects or the current location and even the topological relations of objects, like this. The unseen object might be predicted to be closer to a plate than a mirror or a city, along with the surrounding information that there is a fork and spoon next to it and it is placed on the table. Based on this inspiration, we propose a method to calibrate the zero-shot recognition by using similarity-based contextual information between the target unseen object and its surrounding seen objects. We supplement the limitations of existing ZSL methods, which rely mostly on visual information, by using the surrounding contextual information, and our methods are independent of a specific recognition system. And lastly, we validated the effectiveness of our approach through the experiments. Our proposed model classifies unseen objects with the help of the context obtained from its surrounding objects in a multi-object scene. Several situational assumptions for surrounding objects are provided as follows. They are predicted before the zero-shot recognition of unseen objects and do not belong to the unseen classes. And for each of them, the predicted candidates and the corresponding prediction probabilities are given by pre-trained image classifiers as follows. So the surrounding information of each unseen image xi represents the information about multiple surrounding objects of the unseen object. So specifically, the number of surrounding objects in surrounding information are nsi, and each surrounding object has multiple predicted candidates with the number n cand k obtained by the pre-trained image classifier. I'm going to explain the pre-trained image classifier, um, oh, the pre-trained image classifiers will be presented in the last slides. Anyways, each of those candidates is composed of a pair with its class label and prediction probabilities. The figure on the screen is the overall workflow of our proposed model with the pre-mentioned example. The red bounding box is the target unseen object, and the blue ones are its surrounding objects. Our model works on the two branches. The instance level visual inference module is first applied to a target unseen image, which is a red one, in a multi-object scene. Yeah. It extracts the visual features from the image and predicts classification scores for the target class labels using a zero-shot classifier. And secondly, using the classified results of the surrounding objects obtained from a pre-mentioned pre-trained image classifier, our proposed model then performs the calibration based on the similarity measurement between the target unseen object and its surrounding objects. Similarities are obtained using a hierarchical knowledge graph or semantic embedding space, or both ones. In this example, the correct label of the unseen object, which is the red box, is plate. The instance level inference module first focuses on the red boxed image and predicts that the object is a city with the highest score due to its wide or flat or rounded appearances. However, the pre-trained image classifier for the scene set mostly ranks the potential candidates of its surrounding objects, which are likely to be tableware. It indicates that a plate is more appropriate to be found in the scene than a city, and then results the plate to be first re-ranked. Specifically, the instance level visual inference derives prediction scores on an unseen object for unseen class labels as output. The fully supervised learning is conducted only for the seen class labels and used to measure the compatibility function g, x, y between a given input visual embedding x and an output semantic embedding y. We incorporate our calibration methods into each of several existing zero-shot recognition models, which are SJE, latency embedding, cons, GCN, and we evaluate the comparative performance between the models with and without the calibration algorithm. We apply calibration to a prediction score for an individual unseen object using similarity scores between the class labels of the target object and its surrounding objects. When measuring similarity scores, we consider not only the top one classified labels of surrounding objects, but also all the labels of their potentially ranked candidates. Such use of potential information elevates the problem of identifying misclassified surrounding objects as context. So we propose three submodels based on the measurement of similarity scores, which are semantic similarity, cosine similarity, and the combination of both. At first, the semantic similarity-based calibration method uses a hierarchical knowledge graph, which is an ontology. The semantic similarity-based calibration function, which is HSS, that outputs the calibration score is formulated as follows. Similarity between an unseen class label and candidate of surrounding object is calculated by using knowledge graph, and the prediction probability P for the candidate serves as a reliability serves as the reliability of the calculated similarity. To obtain the overall context for the label CY, we apply the average of the maximum weighted scores, which indicates the combination of the most likely surrounding informations for each of the surrounding objects. We use three path and depth-based measures for the experiments. It will be presented later. Yeah. Those measures are provided by the NLTK library on WordNet. The cosine similarity-based calibration method is generally similar to the semantic similarity-based calibration method, which is previously mentioned, but it uses different external knowledge and a different similarity measurement. We use the cosine similarity to measure the similarity scores of the target class label in this method, and the class labels of its we use the cosine similarity to measure the similarity scores of the target class label and the class labels of its surrounding object on the semantic embedding space. The cosine similarity-based calibration function, which is HCS, is specified as follows. Although our methods are independent of the type of semantic space, we use a word embedding space as the semantic embedding space for the experiment. Yeah. And the last model is harmonic calibration model. This model combines the results of the two previously mentioned methods. It uses both a knowledge graph and a semantic embedding space when referring to the surrounding information. This this harmonic calibration function, which is HAM, can be simply specified as follows with a balancing factor beta for the calibration scores. Given an unseen image X and its surrounding information Si, X, the scoring function f for a specific class label Y can be specified with the combination of visual inference function G and the calibration function H can be specified as follows. We derive the prediction for the class. Finally, we derive the prediction for the class by maximizing the scoring function as a result. The functions, the formulas are explained in our paper more detail, with more detail. Here's our experiments. For the training image data set in our experiment, we used the ImageNet 2012, which is used to train the instance level visual inference model. Out of 1,000 class labels, we only consider 944 class labels which have a semantic embedding available. For the testing image dataset, we use a visual genome dataset which consists of multi-object images. We applied the three criteria in the selection of 34 unseen classes. We selected categories selected from 360 categories in the ImageNet 2010 1K, which is disjoint from ImageNet 2012 1K. Categories representing and next criteria is the categories representing generic objects, and the last criteria is the categories that have more than 20 image instances in visual genome dataset. For extraction of visual features, we used in Inception version 1, pre-trained on ImageNet 2012 1K, so unseen classes have never been used in training this model. And we use 1024 dimensional outputs of the top layer pooling units. For the semantic embedding, we use word vect based on skip-ram trained on Wikipedia with 1,000 dimensions. For the knowledge graph to measure semantic similarities, as I mentioned before, a subgraph of WordNet is used, so the namespace of our class labels is unified into the form of synset IDs in WordNet. Here is our comparative results. We separately apply our calibration methods to the 4 zero-shot recognition baseline models for the evaluation, which are SJE, latent embedding, cons, and GCN. This results in 7 different types of comparative result evaluations per baseline model, which are 3 different semantic similarity measures and cosine similarity and 3 harmonic measures on those semantic similarity measures. The values are measured in terms of the average per class accuracy in percentage. Our proposed model outperforms the others on all backbone baselines when using both classic and generalized settings. Generally, the harmonic calibration methods show better performance than the other calibration methods, as you can see on the screen. In the classic setting, the maximum increase was 51.8% compared to the baseline, and in the generalized setting, the maximum increase was much higher with about 500%. This indicates that the effectiveness of our calibration algorithm is emphasized as the number of categories increase because it induces the prediction onto types of categories that are highly relevant to the context. The similar tendencies can be seen on the top end predictions. For this evaluation, we used the harmonic calibration method based on path semantic similarity measure, which is HMPath, which shows the over best performance. Although the rates of the performance increase in the top 5 predictions are relatively low, but the top 5 predictions still reasonably outperform the baselines. That's the point. Here is our qualitative examples. The figures show the qualitative experimental results of our calibration. This exemplify how the instance level prediction of the existing model is complemented by our calibration with the surrounding information. Among these examples, in the third example, the instance level prediction results the instance level visual inference model cannot predict the ground truth label ice maker even in top 5, but the prediction result was calibrated to rank ice maker first at the first because of the high relevance to the surrounding microwave and refrigerator. There were some cases for such calibrations to bring about negative impacts as well. In the fourth example, a bridge is correctly predicted by the image instance itself, but the fishing rod, which was comparatively more relevant to the surrounding objects, which are boats or bird, so it wrongly took the first place by the calibration. In this paper, we presented novel approaches in ZSL for zero-shot recognition to calibrate an instance level prediction results using the surrounding contextual information. We applied various similarity measures to obtain the surrounding information. We validated our approach with experimental results. For future work, we are considering the topological relation to be analyzed in a multi-object image, and semantic relations in a knowledge graph are possibly considered as well. Thank you for your interest. Please contact my email address if you have any questions. Thank you.